This is Honors Algebra 2 Pre-Calculus. We're back with 9.6 in Pre-Calc. Right now we're on page 666 of the textbook talking about distinguishable permutations. So before we jump into this formula, let's talk about what we mean by this. So how many ways can we arrange the letters in dog? So let's actually go ahead and arrange the letters in dog, right? Instead of doing this as like a strictly theoretical observation, let's actually figure this out. Okay, so if I were arranging the letters in dog, which I'm going to start with up here, right? I could start with D-O-G, right? Dog. I could keep the D where it is and then put G-O, right? I could instead put the O at the front, so O-D-G, right? Or O-G-D, right? There's two ways to make it work with the O at the front, and then I could put the G at the front and make it G-D-O or G-O-D, right? So it turns out that there are 6 ways to arrange this, right? Because I have the D at the front, and then I have 2 different options for how to arrange the other 2. I have the O at the front, and then the 2 different options for how to arrange the other 2, and the G at the front, and the 2 different options. So it turns out there's 6 ways, right? So that's not super surprising because D, O, G are 3 distinct letters. So I have 3 options for the first, 2 options for the second, and 1 option, whichever one I didn't pick for the last. And sure enough, that's 6 ways. So that makes sense, right? Because D, O, and G are all different letters. But now let's talk about how we arrange the letters in mom. So for B, I could start with M-O-M, right? There's an M at the front, and then an O and an M, right? I could put M-M-O, right? The trick is that the 2 M's are not distinct. I don't know which, it doesn't matter which M is at the front. There's an M at the front, and it doesn't matter if this M is that M or that M is this M. It doesn't matter. But let's go ahead and actually pretend like they're different M's. So this is the same M, and I switch those 2. I could start with the O at the front, and I could put M-M, or I could put the O at the front and switch the order of the 2 M's. But notice how that still looks like O-M-M. I could put the other M at the front, followed by O-M, and I could put the other end, that other M at the front, followed by M-O. But what I want you to notice is that some of these are repeat answers. I already have mom at the top. I already have M-M-O at the top, and I already have OM, right? So it turns out that there's only 3 distinguishable permutations, meaning that these 2 are the same permutation because the M's are not distinct items. So it turns out there's only 3 ways to get these values. Now, if there's only 3 items, it's not a big deal. Sorry, ignore the alarm. If there's only 3 items, it's not a big deal that I could write out the possible permutations and then cross out the repeats. But when this gets a lot harder is when I pick bigger numbers, right? So this was still 6 factorial, right? But what happens is, and I'm going to show you the logic of this in a sec, but essentially, I took that 6 factorial, that was the number of ways to get these 6 answers, and then what I'm going to divide by is the factorial of the repeat. So I end up getting that this is a 6 on top of a 2, which is those 3 options. So we're going to walk through this in a second with something slightly larger. So let's pick a slightly bigger word. So same idea, let's pick puppy. So we're going to talk about how we could arrange the letters in puppy. Now you'll notice there are 3 P's in puppy, right? So I already have puppy here, just fine, right? So I'm actually going to, in my brain, call this P1, 2, and 3, just so I can show you the different ways it's going to work. Now, the problem is that there's a ton of different ways that I could arrange all of the other 4 items, right? So the issue we're going to run into here is if I tried to figure out the number of ways to arrange this, it's going to be huge, right? So using the same logic that we just saw in the last one, I see that there are 5 total letters, right? So there are 5 factorial ways to arrange these letters if they were all distinct, but then there are 3 that are the same. If I divide by 3 factorial, I'm going to get that there are essentially 20 distinct ways to arrange this. Now what's crazy is that if I weren't doing, so there's actually a total of 5 factorial, which is huge, right? 5 factorial is 120. So there are 120 ways to write this, right? Because there are 120 ways to write this, 5 factorial. But of those 120, only 20 of them will be unique, and all of the others will be a repeat of one of these 20, right? There will be 20 possible unique ways to do it. So let's walk through what that formula is. So essentially, if we have n items, so this is on page 666, right? If we have n items, but there are n1 of type A, like some type, and there are n2 of some type, right? Some type B and N3 of some type C, right? Whatever they are. So the number of permutations will be the n factorial, right? Which is that n is the total number, right? N is the total number, divided by the factorials of the repeats. So these are the repeats. So we're going to do an example 6 now, where we do it with a word that has lots and lots of repeats. So let's use Mississippi. So in example 6, how many distinguishable or distinct, so how many distinguishable permutations are there of the letters in MISSISSIPPI, Mississippi? Okay, so first thing I have to do is count the total number of letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's going to be an 11 factorial on the top because there are 11 letters, right? But then I need to look for my repeats, right? There's no repeats of M, right? But there are repeats of I. There are 4 I's, so that's a 4 factorial for the I's, right? 1, 2, 3, 4 S's. It's a 4 factorial for the S's, right? And I'm just making this as a note so I know what I've used. And there are 2 P's, so a 2 factorial for the P's. Now you might be saying, but Hogan, why can't I do it for all the letters? Well, you could. There's 1 M, so you could put a 1 factorial on the bottom, but a 1 factorial is just a 1 anyway. So it wouldn't matter if you actually divide by the factorial of each one of those values. It's just that there's only 1 M. So I can type this in a calculator. If I type it in a calculator, I'm going to type in 11 factorial in parentheses divided by, in parentheses, 4 factorial, 2 factorial, and that's fine, right? This is another one of those ones that you could probably narrow down pretty significantly by hand as well, though, right? This is an 11 times a 10 times a 9 times an 8 times a 7 times a 6 times a 5 times a 4 factorial. If you were doing this by hand, I'd leave this 4 factorial to cancel, and then I have a 4, 3, 2, 1, and a 2 and a 1. So I can cancel a bunch of stuff, right? I can go ahead and use this 3, 2, 1 to cancel the 6. And I can use this 4, 2, 1 to cancel the 8. So it seems to me that what I'm typing in my calculator is 11 times 10 times 9 times 7 times 5, which I get is not super fun, but it's survivable, right? You also could have typed the whole thing into your calculator. Either one's fine. So 11 times 10 times 9 times 7 times 5. I get that there are an awful lot of ways to arrange these letters. So 34,650 is my answer. And again, you can get that either by typing this into your calculator, which is fine, or you could get it by typing in 11. So in parentheses, 11 math, go get the factorial, divided by, open the parentheses, 4 factorial, 4 factorial, 2. With 2, I'm kind of lazy, and I kind of didn't want to bother with factorials, since 2 factorials is just 2, but if I do it this way, I get the same answer. So it doesn't matter. So you get, that's the number of distinguishable permutations. Again, the argument is that there are 4 S's, so if you switch these 2 S's, it would still say Mississippi. If you switch these 2 S's, it would still say Mississippi. So that's what we mean by distinguishable permutations.